So this webinar makes up one of a series where we're looking at the development of a motor through its full design cycle. In this webinar, we'll be focusing on the motor's NVH, and I'll start with a brief introduction to motor NVH before looking a little more at early phase NVH analysis in ANSYS MotorCAD and handing over to my colleagues to look at later stage electromagnetic analysis and the later stages of mechanical analysis using ANSYS Maxwell and ANSYS Mechanical. In the earlier webinars, which are available on the ANSYS website, we've looked at the initial design and optimization, the electromagnetic analysis, thermal performance, and most recently rotor stress calculations, and a final webinar will be covering the system integration aspects. The motor design we're showing today comes from the coupled electromagnetic, thermal, mechanical, and NVH optimization of the design to meet an automotive specification covered earlier in the webinar series. So first, a short introduction to motor NVH and the challenges in this design. Motor noise and vibration can be a crucial area to understand and control for any motor or generator. And with an increasing focus on electrified vehicles, this is a very important area for noise, as without a combustion engine providing masking noise, the tonal whine of both traction and auxiliary motors can be much more audible and annoying. Using analysis tools throughout the design process to consider NVH is very important to get to the best solution and to avoid unexpected problems later on. We need the right tools that can combine the electromagnetic, structural, and acoustic response to do this effectively. Often the motor's NVH is only analysed late in the design process when the motor's design has already been largely fixed. This gives a great risk that the problem will be found at a point where it's much harder to solve. And what we want to show today is how NVH can be considered from the start of the motor design process, starting with quick and simple calculations and moving into more detail as the design matures. So as discussed earlier in the webinar series, we set the requirements for this motor and optimize the design to minimize the magnet mass and the drive cycle losses. However, many of these performance targets are really directly opposing what will be ideal for a quiet motor, particularly minimizing things like the air gap size and maximizing the flux density in that air gap. Therefore, when this initial optimization was being carried out, we applied an NVH requirement from that initial stage, as unless this is present, we may achieve our electromagnetic targets, but at the expense of an unacceptably noisy motor. In this case, the optimizers found a solution that maximizes the electromagnetic performance while just achieving the sound power level target that we set. This design optimization did not look at detailed features for NVH improvement, so we can now consider these, ideally reducing the noise while limiting the impact on other performance characteristics. So, following the initial NVH analysis as part of our optimization, what we now aim to do is to understand the noise performance, to explore additional options for noise reduction without significant adverse effect on the other performance metrics, and also increasing the fidelity of the analysis. So what I'd like to talk about first is how we can use ANSYS MotorCAD to consider the noise while initially designing the motor. So ANSYS MotorCAD is a template-based motor design and analysis tool which can consider the electromagnetic, thermal, structural and NVH aspects of the motor design. So at the early design stage, we already have a 2D electromagnetic finite element analysis of the motor, and from this we can calculate the forces on the stator. For the early stage analysis, MotorCAD couples these electromagnetic forces with fast, analytical, structural and acoustic models to get a good initial prediction of the noise arising from vibrations of the motor itself. Fundamentally, what MotorCAD is doing is looking at the vibrations the motor excites in the stator, looking at the stator radial forces, how that excites vibrations and therefore noise. And it's separate from things like torque ripple, which may in turn cause noise in other parts of the system, and can be considered with simpler torque ripple metrics. So looking at MotorCAD's calculation approach in a little more detail, I'd just like to talk through what we're doing. The Maxwell stress tensor method is used to calculate the transient force acting on the stator from the radial and tangential components of the electromagnetic field. These stator forces are then split up using a 2D Fourier transform into different frequency components for each space order. So what do we mean by the frequency components and space orders? So the frequency or time order components define the frequency of the sound produced, and the space order defines the vibrating shapes taken up by the stator. These are both important to look at together because the stator will respond very differently depending on the shape of the force being applied to it. In a simple example, if you had a force which is tending to deform the stator into an oval shape, it's much more flexible like that. But for example, here we've got forces which are tending to push the stator into an 8-lobe shape where the stator is much stiffer. Frequency is also very important, both because it defines the sound frequency that will be heard, and it's also relevant for whether or not we get mechanical resonances in the system. So once we've got these forces, we're able to use those to look at the structural response. The motor has got many different mode shapes, and each mode shape will have a different natural frequency and stiffness. The stiffness and natural frequency both increase rapidly with the mode number. And because the systems are mechanically linear, we can consider the overall response as the sum of many different vibrations, and those can be calculated separately. MotorCAD calculates the stiffness and natural frequency of each mode using an analytical ring model based on the stator and housing geometry. This is very fast and requires minimal additional information beyond the basic motor design parameters. So from this, the vibration velocity is calculated using the force, the stator stiffness, the excitation frequency, and the natural frequency. So this allows us to split the force up into its different components to understand the structural response to all these different components and giving us the vibration velocity. From the surface velocity, we can then calculate the acoustic power. There are two levels of calculation that can be used for this. Simplest is the equivalent radiated power ERP, simply based on the vibration velocity. And also the far field noise can be predicted using the infinite cylinder method, which includes the frequency dependent sound radiation efficiency. Particularly important for lower frequency noise where the ERP can substantially overestimate the actual noise power. So the spectrogram and order tracking plots rapidly show the sound power at each frequency and can be used to find the dominating space and frequency orders. And we'll look at that a bit more later on with this specific motor. What we're also able to do is export sound into ANSYS Sound, and we're able to replay the sound, apply transfer path filters, and combine with masking noise, as well as looking at more sound quality metrics. So moving back to this specific motor design, what can we understand about its noise characteristics and how can we potentially improve them? As is often the case, we can see that in this motor design, it's the breathing modes where the stator vibrates radially in and out around its circumference that are dominating the noise. The forcing of this arises from the variation in the field all around the stator as the field concentrations align more or less with the slots, changing the mean inwards force when averaged around the circumference. Because of the winding characteristics, we get excitations once every 2 slot passing periods. So in this case, this is 6th electrical order, as well as once per slot passing and higher multiples of this. And it's these components which in this case are giving us our dominant noise, particularly in the higher speed region. One measure often used to reduce noise as well as to reduce torque ripple is skew. So in this case, skew's already been implemented, but despite this, the noise is still quite high. And if we look at the forces, we can understand this a little more. The different skew slices are at a different angle relative to the stator, and therefore are loaded by a different effective electrical phase advance, and this affects the force on each slice. In this case, in the region where the noise is highest, the forces are different in magnitude between the slices, and therefore even with ideal phasing between the different slices, can't cancel out effectively. So looking at other ways of reducing the noise, we can add features to the rotor or stator to reduce the variation in mean radial force as the rotor rotates. In both cases, the aim is to reduce the variation while trying to limit the effective increase in air gap size, as this will reduce the electromagnetic performance of the motor overall. Looking first at an example of a rotor notch, we can see that this reduces both our main peak and some of the lower speed noise peaks. And what this is doing is by reducing the rapid change in force as the field concentration around the end of the magnet passes the stator tooth and slots, it's reducing that breathing mode forcing and therefore slightly reducing the magnitude of the noise. Similarly, we can artificially increase the effective number of stator poles as seen by the rotor field by introducing additional slotting into the stator. In this case, it didn't have a very significant effect, but its effect depends on the motor design and particularly the operating point. And actually, in this case, if we've been looking at an unskewed motor, this would have actually given quite a significant improvement in the noise. So looking at these, it's always very case dependent, which is where this analysis comes in. So combining the different geometric changes, we can achieve around a 5 dB reduction in the predicted sound power level. Of course, there's some trade-off with the other metrics, as what we're doing is affecting the effective air gap size. But really, this emphasizes why it's so important to consider the MVH in the initial optimization and design trade-off, as there are strong interactions between the design for MVH and other performance metrics. And if we can ensure that we start with an acceptable design, rather than one where later in the process significant redesign is needed, that will both reduce the overall project risk and also lead to a better overall solution for all metrics. So I'll now pass over to my colleagues to talk about the additional electromagnetic aspects using ANSYS Maxwell.
Okay, thanks, James. Our first investigation into the kind of high fidelity analysis of motor performance impact on NVH is at the system level, including circuit effects of a variable speed drive. So the variable speed drives utilize pulse width modulation to vary the voltage and frequency throughout the machine's various operating points to achieve the desired effects such as MTPA or max torque per ampere. These higher carrier harmonics or the frequencies from this drive can induce additional harmonics in the winding currents and the resulting torque, as shown in the currents below, without PWM excitation on